Insects are among the most ubiquitous and visible life forms on Earth, and their correct depiction can breathe life into many graphical applications. As part of its work, we present a biologically based method to analyze, evaluate, and simulate insect swarms. In addition, our method can also assist artists in creating such animations. As a first step, our data-driven process extracts three distributions. Because of the zigzaggy nature of the trajectories that can be found in the data, we segment those trajectories into a series of linear segments. The first two distributions that we extract are then the distribution of the lengths of those segments as well as the distribution of turns between consecutive segments. And the third distribution is the density of insects at each point in the swarm. Then, to simulate the insects among several possible collision avoidance algorithms, we choose the one that can best replicate the behaviors of the insects on the previously segmented trajectories. Once a collision avoidance algorithm is chosen, we sample intermediate waypoints from the length and turning distributions, thus replicating the noisy nature of insects' movement at the mesoscopic level. To ensure realism at the swarm or macroscopic level, we aim to replicate the previously learned density distribution. To do this, we make sure that the intermediate waypoints satisfy the Metropolis-Hastings criterion with respect to the density distribution. The resulting simulations are then both statistically correct with respect to the noisiness of insects' trajectories and realistic as far as densities are concerned. Here are the errors between different collision avoidance algorithms and the reference data, normalized for easier viewing. We optimize the algorithm's parameter sets to decrease this error as much as possible and then select the algorithm with the lowest error. In this case, it would be the Orca algorithm. Simulating the noisy nature of insects' movements can be done with a random method, but the generated trajectories may not necessarily look convincing. On the left here, if you follow any one single insect, its trajectory may seem too smooth. In fact, some parameters may need to be configured. Thanks to the distributions we learned, we bypass this tweaking issue and can generate trajectories that are statistically correct in their noisiness. With the addition of the density fields extracted from the reference data, we can also constrain the shape of the swarm on the left to reproduce the real swarm on the right. We can now check if this density is well reproduced. You can see on the two top clips that, unsurprisingly, the random and mesoscopic waypoints methods can't reproduce the density fields well on their own. On the bottom left clip, however, with the macroscopic Metropolis-Hastings criterion, we can reproduce the actual density of the swarm quite well, which you can see on the bottom right clip. Next are two often used metrics results. On the left is the average distance of the insects to the centroid of the swarm. Again, unsurprisingly, the random and mesoscopic waypoints methods, in red and green, on their own lead to erroneous spatial distributions of insects. This is corrected thanks to the macroscopic shape constraint, which allows us to approximate the reference data. On the right is then the polarization factor, which quantifies the collective behavior of the insects. Our mesoscopic method is already better than a pure random method, and is then even closer to the reference data after adding the macroscopic shape constraint. The multiple results for both metrics here represent different precisions for the discretization of space which is needed to extract the density fields. Our method can also be easily integrated with existing global path planning algorithms as shown in this next example. Here a swarm of insects is made to travel to successive light sources while also avoiding pillars. As our approach can also assist artists in generating insect simulations, the user has a fair amount of freedom with this pipeline. For instance, the sketch depicting the desired density field of the simulation can be arbitrarily defined, here in red with a darker color representing higher densities. In blue you can see what kind of trajectories can then be expected. This sketch has no density at the center. This is where you would put an obstacle, for instance, as shown in the next animation. With this kind of input, we can then easily generate other types of trajectories at other scales and with other species. In summary, we propose a biologically inspired approach for the simulation of insects. We automatically select and configure the best suited collision avoidance algorithm and combine it with methods that generate trajectories that are statistically correct with respect to local and global swarm features. Finally, we can assist artists in creating simulations from simple sketches or retargeting existing ones.